Hello and welcome to all of you. My name is Mridul and I am an alumni from NIT Warangal. Today we are going to discuss on the topic called electrical machine, which is a core subject for electrical engineers in GATE. Okay. So this topic, electrical machines, you see the weightage of this subject is more than 10 marks. Okay, it's more than 10 marks. It's 10 plus. If you see the average of this subject for the last 10 years, you will see it's around 10 to 12 marks, which is nothing but you can see it's just 10% of the complete syllabus. Okay, which is very high. And the importance of this subject does not end with the GATE. You see, even if you go for PSU interviews, each and every PSUs, okay, or even the if you go for higher studies, even those in those colleges, if you go for IITs or IISCs, the interviews that are conducted there, everywhere it is expected that an electrical engineer will be good with the basics of electrical machines. Okay, so this is a very important subject, and today we are going to start with the basics of electrical machine. We will understand the agenda of this particular video course is to understand the basics of electrical machine. As we all know that electrical machine course for GATE consists of 4 main topics, which are transformer, DC machine, and AC machines. In AC machines, we study 2 types of machines, which are induction motor, and an induction motor also we study 3-phase as well as single phase, and synchronous machine. So this is a compact syllabus of electrical machines, okay, for GATE. Now you see, to understand these topics, we need to understand the basics from where these machines are evolved. What is the relation of this machine? Now the basic problem which we face while studying is, or the basic mistake that we do is, without understanding the relation between these machines and what is, from where they evolve, what is the principle, we directly go to these machines and start studying the concept of these machines, and we study these machines in a discrete way. That means, I have heard students saying that I will prepare only DC machines, or somebody will say I will just prepare transformer for GATE and I will leave rest of the AC machine, or somebody will say I will prepare AC machines, I won't prepare DC machines. So you see, the first thing or the first advice from me is that you have to understand the relation between these machines. Okay, and if you see the relation, they all come from the same principle, which is called electromechanical energy conversion principle. Okay, so today's topic, what we are going to do is we are going to understand what is the relation between them and from where these machines have evolved. Okay, also what we are going to do is we are going to understand the basic laws, okay, which are required to understand this particular machines, and the conventions which are required. For example, right hand curl rule, Fleming's left hand and Fleming's right hand rule. When we talk about the laws, we talk about Ampere's law, we talk about Faraday's law, we talk about Lenz's law. So these are all 3-4 laws that we will talk about, and those are the laws which are required. Okay, we will concentrate only on those laws. Okay, and whatever laws we discuss today, you will see all the 4 machines will only be dependent on that particular laws. Okay, will not go outside that. So let's see what is the need of electrical machines first. You see, human beings need power or an energy to survive. Now there are very different forms of energy, for example, electrical energy, heat energy, mechanical energy, etc. and etc. Electrical machines, for electrical engineers, those particular energies which we are concerned about are electrical energy and mechanical energy. These are the two energies that we are going to deal with. Mechanical energy. Now what electrical machines does basically is to convert this energy, electrical energy, to mechanical energy, or mechanical energy to electrical energy. Okay. Now that particular machine which converts electrical energy to mechanical energy, we know it as motors. Similarly, that particular machine which converts mechanical energy to electrical energy is called as generators. Now that may be AC generator, that may be a DC generator, depending on its construction as well as principles, which we will see later. Okay. Also we will study transformer. What is transformer? Transformer converts electrical energy to electrical energy itself, but it changes the power level, not the power level, the voltage levels, okay, and the current levels, but the power remains same for transformer. So you see, all the machines that we are going to study will be dependent on one principle, that is called electromechanical energy conversion principle. Now what is this principle? This principle is based on the conversion of both these energies. Now what this principle says is that you cannot directly convert electrical energy to mechanical energy, or you cannot convert mechanical energy directly to electrical energy. What you need is a intermediate, and that particular intermediate is known as coupling field. Okay, you need an intermediate, and that intermediate is called coupling field. Okay. Now what this coupling field does? Now what this coupling field does is it stores the energy. Suppose, let us take an example of, say, motors. Now what happens in motors? In motors, what is the input? The input in motor is electrical energy. And what is the output we expect in motors? In motors, we expect that the output will be mechanical energy. Okay? We want rotation. Now, how this is achieved, let us understand. So, what happens is, this particular electrical energy will be input to this coupling field. Now the function of that coupling field will be storing this particular electrical energy. Okay, as well as this the first thing is storing. It should be able to store the energy. Okay, storing energy. First, this should be the first need of this coupling field. After storage, what will happen is it should react with the mechanical energy. It should react with the mechanical energy. When I say it reacts, it means that the energy which is stored here should be able to drive this particular or convert into mechanical energy. Okay. Now, how this is possible? This can be done by two types. I mean, this coupling field can be realized by two things. We know there are two types of energy storage elements in electrical engineering. That is capacitors and inductors. So, let us find it again. So what I want to say is, this coupling field, okay. Now let us talk about this coupling field now. So one thing we have understood is whatever is doing, this coupling field is responsible for whatever is happening. This energy conversion thing, complete thing is, whoever is responsible is this coupling field. So let us understand this coupling field. So what I am saying is that this coupling field can be of two types. First type is electric field. It means this coupling field can be realized by capacitors, okay, and this capacitors is nothing but an electric field, so it can be realized by capacitors, okay. The second thing, or the second type of realization of this coupling field is magnetic field. Now there are many ways to create a magnetic field, which we will see later. Now the difference between them is, you see, this electric field, the energy that is stored in this electric field is less than the energy that can be stored in this magnetic field. So in the complete course of electrical machines, we will go with this magnetic field, okay. So in electrical machines, the coupling field which is preferred or which we choose is this magnetic field. Why? Because this can store more energy and thus it will have more force generated in the mechanical energy on the mechanical system, okay. So we will go with this mechanical field, magnetic field, okay. Now this magnetic field can be of two types. Magnetic field can be generated in two ways. If you can see in your PPT, you will see that there are two types, which is singly excited magnetic system. Singly excited magnetic system. Single excitation. Okay, or I can write it down, single excitation, and one more type is double excitation or doubly excitation. Double excitation. The example of single excitation is, simple example we can take as relay. Okay, what happens in relay is, we take a electromagnet, okay, and we make sure that the mechanical force is produced due to the path of the flux. We will discuss this terminologies later, but I am just showing you what is the application of this particular field, okay. So let us not go into the terminologies now. After we discuss the basics of what is a flux and how a field is created, then we will come into this topic and then you will realize how things are happening. So for now, you see, by having a single excitation magnetic system, we have examples of relays or reluctance motor, double excitation system examples are DC motor, DC shunt motor, synchronous motor, okay. So these are the examples of single excitation and double excitation of magnetic fields or magnetic system. Now, to understand this particular concept, you have to understand how a magnetic field is created, or what is a magnetic system and what is electric system or electric field. You have to understand the difference and the analogy between them. So for that, you have to understand, you have to have the basic understandings of EMT, okay, electromagnetic fields. So whatever concepts are required to understand the electrical machines, we will be discussing it right now, okay. So let us start with that. before that, let us wrap up this particular principle. So what we have learned in this principle is that if I have a electrical system and I want one mechanical output, I need a coupling field. And that coupling field will help me to change my electrical system or electrical energy to mechanical energy or mechanical system. To change into mechanical energy, we can tell. Okay. One more thing is, now if I have a mechanical system, and I want the energy of the mechanical system to change into electrical energy, the same coupling field will be helping me to change this mechanical energy to electrical energy. Okay, so this is what we have learned. Also, you see, we can say, let us take an example, say the energy that is given here, let us take the example of motor where the input is electrical energy. So let us say the electrical input energy is WE here. Okay, the field energy that is stored here, we can write that as WFL. That means the energy which is stored in this field. Okay. Also, there will be some losses in this field. There will be some losses in this system also. There will be some losses in this system also. And ultimately, we will have an output which is mechanical output. Okay. So by this principle, what we can say is WE is equal to WFL plus WM plus all the losses. Okay. Now this is for motors. This is for motors. Similarly, for generators, the input will be mechanical force or mechanical torque or mechanical energy. So what we can do is, we can just, for generators, what we will do, we will interchange the position. Okay, this is for generators. So this is what the principle says. Okay, so going further, let us understand what is an electric field and what is a magnetic field, or in other words, electromagnetic fields. Okay, so to understand the basic laws, we have to have a little bit knowledge of EMT, which I am saying again and again. So the first topic let us take is electric charge. Electric charge. Now what is electric charge? We have heard this particular word or this particular term, electric charge, from say class 5 or 6 or 7. Okay, we have heard about this topic. We know we have heard about atoms. Okay, and we know that atoms are made of different types of particles. Out of that, we know that atoms mainly consist of electrons, protons and neutrons. Out of that, we know that electrons are negatively charged. Okay, and the charge of electron is, if you can see in your PPT, is minus. It's minus 1.6 into 10 to the power minus 19 coulombs. Similarly, the charge of protons, okay, is same. The numeric value of charge of the proton is same to electrons, but this is negative 1.6 into 10 to the power minus 19 coulomb, whereas this is positive 1.6 into 10 to the power minus 19 coulomb. Okay. Now this is all about charges. We take this as negatively charged body, and this is positively charged. Okay, electrons are said to have negative charges. The second important concept is electric current. Electric current. What is electric current? This is also a very familiar term for electrical engineers or for any science student. Electric current is nothing but flow of charge, or in other words, we call that as flow of electrons. We know that protons cannot flow because they are situated in the atom, in the nucleus of the atom, whereas the electrons revolve around the atoms and in the orbits, and and given a electric field, this electrons can flow, okay, for certain types of materials. So in other words, what you can say is, we can summarize that electric current is nothing but it is caused due to flow of charge. Now what charges flows? We know that electron flows. But you see, direction of electric current will be opposite to the flow of electrons. Okay? So direction of current is opposite to flow of electrons. I know most of you all, or I hope all of you knows this, but even though I'm just going through this basic topics, okay? The second topic is, or the third topic, which is important, is to understand what is electric field, okay? Now let us say the electric field for point charge, okay? Electric fields of, say, point charge. Now, suppose I say that a body is, say, positively charged or negatively charged. Let us say negatively charged first. I say that I have a body which is negatively charged. What does that mean? What it exactly means is that particular body or that particular group of atoms, a body is nothing but a group of atoms. Those group of atoms have excessive electrons in them. Okay? Excessive electrons in them. So whenever a body has some excess electrons in them, it is said to have negatively charged. Okay? Now suppose there is a body which is negatively charged. Now when it's, say, point charge, that means a very unit negative charge. Now what will be the field for that? Field means, you see, if I have a positive charge here. Now what does this positive charge means? This positive charge means this is deficit of electrons. That means it has less number of electrons. Okay? It has less number of electrons. So you see, now if these two are kept in front of each other, okay, we know that they are going to attract each other. Since this is negatively charged and this is positively charged. And this particular law is given, or we know this particular law as Coulomb's law. We also know that they will have, they'll have equal and opposite forces. Okay? We can also calculate the forces for these two particular charges. Okay? Now, these lines of force, okay? These lines of force, you see, for this negatively charged, what happens is, now this electric field is nothing but there will be force, lines of force coming out from this particular bodies. You can see in your PPT also, if they are isolated, what will happen is, this negatively charged, the lines of force that will come, that will be around this negatively charged, will be coming inside. And for this positive charge, the lines that will be coming outside. Okay? Now, this is also called divergent. Sorry, this is called, negative charge is called convergent, and this is called divergent. because it is diverging. This field is diverging, this is converging. Okay? So this is electric field, as we know, for point charges. There is also a link in your PPT, and you can go to the link for further realization or further study of that particular topic. The next topic is magnetic field. Magnetic field. Now if you see in a PPT, there are various causes or reasons for which magnetic field can be produced. The first which is given in your PPT is current in a wire. So if there is a current in a wire, we will have magnetic field. A loop of wire will also have magnetic field. A solenoid will also have magnetic field. A bar magnet will also have magnetic field. Bar magnet means permanent magnet. Earth, our earth itself has its own magnetic field. Okay. Now, the thing is, what are the causes of this magnetic field? The causes, the primary cause of this magnetic field, if we want to create a magnetic field, we will say that first cause is due to moving electric charges. You can see it in your PPT. Moving electric charge. So moving electric charge will give rise to magnetic field. Okay. Now, once a magnetic field is created, this magnetic field lines will be closed lines. Okay, and once this field is created, we will have two poles, which is called North Pole and South Pole. We cannot have isolated poles as we can have isolated charges as in electric field. We can have isolated positive charge, we can have isolated negative charge, which we have seen the example, but whenever we talk about magnetic field, we will have North Pole and South Pole together. That means a monopole cannot exist. Now let us talk about the Earth's magnetic field. Okay, all of you have seen the Earth's magnetic field. The photo, you can see that there is a picture of the Earth's magnetic field in a PPT. And as we all know that there is a magnetic field of Earth, but how come Earth has a magnetic field? What is the reason behind that? The reason behind that is, we know that, so this is the axis of rotation of our Earth, which is tilted, and we know that the Earth rotates around its own axis and it revolves around the Sun. So what happens when it rotates around its own axis? Okay, it's rotating around its own axis. Due to that, some swirling phenomena occurs. Okay, swirling phenomena, it says swirling whirlpool phenomena. It means you have seen this example of say current. Okay, or you say you take a bucket of water, you put your hand inside and you try to rotate it and you leave it, you will see there will be a whirlpool which will be created in that bucket. Similarly, in that Earth, there are molten irons here, molten irons in this Earth crust, and whenever this Earth is rotating itself, this molten irons are a whirlpool or a molten iron whirlpool is created in these two places. Okay, due to this rotation. And what happens due to that is that electric current is generated. Okay, here electric current will be generated, and due to that electric current, what will happen is we'll have some fields which is generated, magnetic field is generated, and ultimately due to this magnetic field and due to this whirlpool motion, electric current, everything will give rise to two poles which we know as North Pole and South Pole. Okay, that is what we can say. So this is the reason why we have North Pole and South Pole in our Earth. Now the properties of this magnetic lines. The properties is they form complete closed loop. Let us take an example of a bar magnet. Okay, a bar magnet is something like that. There will be a bar here One side of the bar will be north pole, the other side will be a south pole. Now they form complete closed loop. Okay, that means if a magnetic line or magnetic field starts from, say, this particular point, it will form closed loop. Okay? This is how this loops is going to be closed. Okay? So in this way. Now this is going to be, this is a 2D picture, this is going to be in a 3D way. This is going to come out from every possible directions of that particular bar. The second point is they do not intersect each other. Now this magnetic field which is coming out from here, it is not going to intersect the other magnetic field. It's not going to intersect. They will have their own path. Okay? This is important. They won't intersect each other. Third important point is, these magnetic fields have directions. That means, when it comes out from north and it enters through south outside the bar. Okay? That means this field comes, or in other words you can say this goes from north to south outside the bar, and from south to north inside the bar. So north to south outside the bar, south to north inside the bar. This convention will be followed whether you go for a bar magnet, whether you go for an electromagnet, it doesn't matter. This particular concept is going to be followed everywhere. Okay? Or this particular rule, or we may say this is a convention. We'll always follow this convention that magnetic lines will flow from north to south outside the bar. Okay, if we have a electromagnet, for example, you may take the example of DC machine. Most of the time I find students confusing how the lines flow in DC machine. Suppose I have a DC machine in this way, and I say this is north pole and south pole, and lines flow from this north pole to south pole in this direction. What happens is, this is an electromagnet which is caused by some, say, conductors are there. I can color the conductors with some. So these are my conductors, or say electromagnet. I've created this electromagnet. So what happens is, you see, this is a core, this blue, this is my core. Okay. Now what I have said is that electric fields will flow from north to south outside the bar. Now see, this is my bar. This is my bar. So it will flow from north to south outside the bar, say from north to south outside the bar, and from south to north inside the bar. And this is also called the flux lines. Okay? So this is how the magnetic lines or magnetic field is present in a DC machine. Okay? So this is important. The direction is very, very important. Now the fourth point is they behave as elastic. This is also a very, very important point. That means you can take the example of a rubber band. If you have a rubber band in your hand, okay, between these two fingers, and if you try to press it, what it will do is, those rubber bands will try to push you back, okay, to its normal position. So in that particular way, suppose, let us take an, let us take a path. Say I have a north pole and south pole, and they are flowing through this path, but suppose the path, this is a normal path. Let us say this path has high reluctance. Now reluctance is something which will oppose the flow of path. Is similar to the flow, similar to resistance, how resistance opposes the flow of current. Similarly, reluctance will oppose this flow of magnetic field, okay, or we say flux, flow of the flux. So this was the normal, this was the normal path. Now suppose there is some other path which is making it flow through this, because this path has lower reluctance. So lower reluctance. Now what will happen is, what it will try is, it will try to come down to this particular position. And from this principle, we have derived a motor which is called reluctance motor. What it happens is, we have used this particular theory, okay, to derive an electrical reluctance motor, which is, suppose we have an electromagnet, and from that electromagnet, let us say this is an electromagnet. We have created, due to electromagnet, say we have created a north pole and south pole here. Now suppose I have blades positioned, let us draw it in a proper way. Say this is my blade. Okay. This is my north pole and this is my south. So as we know that electric lines or fields are going to come out from north, so they will come out from this north, and see, my flux will flow through minimum reluctance path, and it is similar to how current flows through minimum resistance path. So you see, air has more reluctance, whereas this particular iron, and say this particular rod is made of iron. Now iron definitely will have less reluctance, okay. So what this flux will try to do is, this flux from here, it will try to go through the minimum reluctance path. That means through this path, right? It will try to go through this path. Now you see, it is behaving. Now if there was no, say there was nothing here, so ultimately how would they have been? The flux would have been in this way. They would have flowed in this way, this particular path. So what this particular flux will do is, they will try to come back to this normal position, okay. So a force will be experienced on this particular say bar or this particular iron piece, okay, in this way, and this will experience a force in this way, and they will rotate, okay. Once we have a motion, it is going to rotate. So this particular, by applying this particular concept, this reluctance motor is derived, okay. So this is the third or fourth property of the magnetic field, which is they behave as elastic, okay. And the fifth property is also similar to this, or it is derived from the same thing, which is they try to flow through the minimum reluctance path. So these are the five properties. So these are the five properties of magnetic lines of force, which is very, very important for us to understand. The next terms which I would discuss is MMF. If you see in your PPT, the terms are MMF, magnetic flux, and reluctance, okay. So first of all, let us see what is MMF. Now MMF means magnetomotive force. Now what is this force? It is the property of certain substance, or it's a phenomena, you can say, that gives rise to magnetic field, or in other words, due to this magnetomotive force, this magnetic field is generated. Now we have seen that in electric, that means in electric field, we know that current flows due to EMF or electromotive force. Similarly, we can relate this analogy here. That means MMF can be written as F. This, due to this, we have flux field of line, and it is given by number of turns of a coil. If it is generated in a coil, number of turns of a coil into the current flowing through the coil. It is also called M into I. Okay, so the unit of this is ampere turns. Also, we can write this as flux into reluctance. This is reluctance. We can denote the reluctance as S, okay, so that we do not confuse with the resistance R. So what I am saying is, we can denote the reluctance as S. So F is phi into S. Okay. So this is all about MMF. The next topic is magnetic flux. Okay. So what is magnetic flux? We have seen what is magnetic field. So magnetic flux is a product of the average magnetic field multiplied by the perpendicular area that it flows through, okay, or you may say it penetrates. Okay, that means magnetic flux phi can also be given as magnetic flux density B, magnetic flux density into area. Okay, or in other words, if you want to have physical realization of what is flux, flux is nothing but, suppose we have an area and this is the number of magnetic fields, field line of force, okay, and this, suppose the area of this is A and this is perpendicular to this field, so I can say this is B into A. Okay, if this is not perpendicular, we'll have a B. If this is the direction of my B and if this is the direction of my A, then I can have a vector relation of this phi. For now, let us say it is perpendicular and we will take it as B into A. Okay, so this area is a perpendicular area and B is the magnetic flux density. Okay, the next term which we are using again and again is reluctance. Now what is reluctance? Reluctance is similar to resistance. Reluctance is similar to resistance. What happens to resistance in electric circuit? In electric circuit, resistance R, it is the property by which it resists the flow of electric current. Similarly, reluctance S is called the property of a material to to resist the flow of this flux, magnetic flux. Okay, so you see R is given by, we know R is, resistance is given by rho into L by area A. Similarly, S is given by L by mu into A, where mu is the permittivity of that material, okay, which can be calculated. Now there is one more difference between, there is a very important difference between reluctance and resistance. Okay, this is very, very important. That is, in resistance, energy is dissipated. Energy dissipates. Okay, whereas what happens in reluctance? In reluctance, the energy is stored. Energy is stored. And here, electrical energy is dissipated. Since it's an electrical circuit, so electrical energy, you can mention it. Electrical energy will be dissipated. Here, magnetic energy is stored. Magnetic energy is stored. Okay, this is important. Let us understand the next topic, or we have seen the analogy between electric field and magnetic field. So, let us see the analogy between the electric field and magnetic field now. Electric circuit will be given by, this is my EMF, say, okay, and I have a resistance here. So current will be flowing, this is my EMF, and EMF I can give it by I into R. Similarly, if I have a magnetic circuit, so magnetic circuit can be represented by this is my reluctance S, flux will be flowing due to this MMF, which is called F. Okay, so F will be flux into reluctance. Okay, so this is the analogy between electric field and magnetic field. Now see, the current flows through the minimum reluctance path, whereas this magnetic flux flows through minimum reluctance path. There is a similarity. Now we are done with the basic terminologies of electric as well as magnetic fields. Now what? Now what is there else to understand for electrical machines? Okay. The next important thing is to understand the relation between electric field and magnetic field. Okay. You see, it was a breakthrough in 1819th century. Okay. Before 1800th century or the starting of 1800th century, it was believed that the electric field and magnetic field, there is no relation between them. And it was a very strong belief. Okay. Now there was a scientist called Hans Ørsted. Okay, and he gave a statement. He said that no, there is a relationship between electric field and magnetic field. And you see, due to that, all the laws that we see, all the Faraday's law, Ampere's law, Biot-Savart's law, whatever law you take and whatever this complete advance of our technologies, whatever we are having today, is because of this breakthrough relationship. And this relationship says that, okay, the first relationship. So what I am saying is that we will try to derive what is the relationship between current and magnetic field. Current and magnetic field. So the first relationship was given by Hans Ørsted. What did he say? First relationship. He said that a steady current produces a steady magnetic field. A steady current produces a steady magnetic field. Okay. Now let us understand that this is a breakthrough. Okay. So let us visualize also. Now for this particular statement, what does steady current means? It means I have a conductor and the current flowing through that is, say, steady or constant. So this is a conductor. So this is a conductor and it is having I current in it. Okay. This is my conductor and it is having I current flowing through that conductor. Now let us see how will be my magnetic field. To find out the direction, we use a convention, we call that convention as right hand thumb's rule. That means we will take this right hand, will direct the direction of my thumb will be the direction of the current. So if this is the direction of my current, this will be the direction of my thumb. And these four fingers, this direction of my fingers when I point the thumb towards the direction of the current will give me the direction of the magnetic field at any point. That means, say this is the conductor and the current is going upwards, so field will be in this way. That means if you see in this way, it is going inside. At this particular point, it is going inside. We can denote it by cross. Similarly, at this particular point, it is coming out. That means we can give it by a dot. Or in other words, we see this is the direction. Okay? This is the direction. So, we can also see it in other view. That means there can be other view also. Suppose say the current is coming out. Say the current is in this direction. It is coming out towards you. Okay? So if it is coming out towards you, that means my thumb is directed towards you. So I can say that my field will be anti-clockwise. Okay? My field is anti-clockwise. Similarly, if I have a conductor which is having a current inwards, that means my thumb is now towards the direction of the board. So if that is the case, then the direction of my field will be clockwise. So this particular convention is called right hand curls convention or right hand thumb's rule. Okay, you can refer it in your PPT. Now, this is the convention for this particular statement. On this particular statement, we have a law also. We call that law as Ampere's law. Okay, you see what that law does is, suppose we need to calculate the strength of this particular field. Okay, now strengths of field can be calculated, or strengths of field can be denoted in two ways. That is, first is by H or by B. Okay, what is H? H is denoted for magnetic field intensity. What is B? B is magnetic flux density. Both these terms represent the strength of the field. Okay. Now if we need to calculate the strength of field in terms of H for a steady current and a straight wire, straight conductor, we can use Ampere's law. Ampere's law. Okay. There is one more law which is more generalized way, generalized version of this Ampere's law is called Biot-Savart's law. Now you will study all these laws in EMT. What I am trying to show you that from where these laws have evolved. Okay, so these laws have evolved from this particular statement. Okay, so these laws depends on this statement. That means Ampere's law and Biot-Savart's law is only applicable when I have a steady current. When I have a steady current. Clear? This is very important. You cannot apply Ampere's law or Savart's law if the current is not steady, or in other words, a changing current. Now, we can apply this right hand curls rule, okay, right hand thumbs rule, and find out what is the magnetic field that is created for a solenoid. Okay. If you see in your PPT, let us say this is a coil. Let's take this example. And current is flowing through this in this direction. Okay. So you see what is happening is, now this is wounded. This particular coil will be wounded on, say, in this direction. Say in this way. Okay? Now what will happen? So this is what the actual situation, and this is, I am showing the direction of currents in that particular coil. So this is the actual direction. So what is happening is, if you see at this particular points or at this particular point, current is going inside. You see current is going inside at this particular point. And at this particular points, if you see, current is coming out of the coil. So you see current is coming out of the coil here. Here current is going inside. So this is what is happening. Now that means I can say that if there is a bar here, if there is a bar, this bar is nothing but this particular bar. So what is happening around this bar is, I am having dot and I am having cross. The direction of currents is something in this way. Okay. Now we have just now seen that by right hand curls rule, we can give or find out the magnetic field due to this types of current. So if current is coming out, that means towards you, then it is going to be anti-clockwise direction. That means the field due to this is anti-clockwise. And this all together, this side, left side together, will make a field which is in this direction. Okay? Similarly, this side, this right side, will make a field clockwise. That means this will be, say, clockwise. So this side is, say, clockwise. Okay? So this is the situation here. This is the situation here. So you see, now this is similar to a bar magnet. So if I have a bar magnet, say N and S here, and what will happen is the field will come out from north and go inside the south in such a way. Similar thing is happening. Field is coming out from these directions. Okay. This is anti-clockwise, so fields are coming out in these directions. It is going inside in these directions. Here it is clockwise, so it is coming out from this and it is going inside through this. So I can say that this particular point is nothing but my north pole, and this particular point is nothing but my south pole. So this is how a solenoid or a coil or an electromagnet, whatever you say, due to this current carrying coils, okay, we will have north poles and south poles. This is how, and this is why they are created. So again I will repeat the statement which you have understood here is that the first statement is a steady state or a steady current produces steady magnetic field. Okay. Now let us see what else can be said between magnetic field and current. So after Hans Ørsted in 1819 he gave this statement. Then many scientists started experimenting on this particular statement. Okay, there is one more scientist whose name is Faraday. What he started experiment was whether the reverse is true or not. So the reverse is, if I have a steady magnetic field, can it produce steady current? Yes or no? A steady magnetic field can produce steady current or not? And he did this experiment. He went up to do this experiment rigorously for days and days, okay, but he was not successful. Okay, what he found out ultimately that a steady magnetic field cannot produce steady current. It cannot. Okay, but eventually one day, accidentally what happened is he discovered something. What he discovered is, due to sudden changes of this field, that means when he switched on or switched off this particular electromagnet, what happens? There was a change in field, and due to that change in field, there was an emitter connected across a circuit where he was trying to see whether the current is flowing or not. What he saw is, whenever there was a sudden change in this magnetic field, there was current. And ultimately he came to experiment, he came to some conclusion, and he did the experiment in a better way, and ultimately he gave a relation, okay, and you can see that relation in your PPT, that says that a steady magnetic field can produce current when the conductor is moving in that magnetic field. Okay, or in other words, that conductor is cutting the fluxes. Okay, or flux cutting action takes place. Okay, similarly, if I have a steady current, then what will happen? If I need to, or in other words, if I have a change in magnetic field, then I can produce a steady current here. So there are two states. First of all, I can write that a steady magnetic field shall produce current in a moving conductor. That means if I have a steady magnetic field and I have a moving conductor, okay, if I have a steady magnetic field, that means it will be something like that. And in this, say this is a field, and I have a conductor here which is connected, okay, or it is closed loop conductor is there, and it is moving in this particular field in this direction. It is going here after some times, it is cutting this fluxes. Okay, so what will happen is current will be produced here. Okay, current will be produced. So this is what he has seen or experimented. What he did is, he had a loop, a conductor loop, and there he connected an ammeter, and in that ammeter there was deflection whenever he was cutting this or moving this conductor in a particular steady magnetic field. Similarly, if he had a changing magnetic field, changing magnetic field. Now when I say changing magnetic field, that means the current which is creating this magnetic field is changing. That means, suppose I have a electromagnet or a coil here. Suppose a coil is, and I am connecting it to a AC source. Now AC source, the current in the AC source will be alternating, due to which the magnetic field which will be created in that solenoid or electromagnet will be changing with respect to time. Now if I have this type of field, okay, and if this type of field links with a conductor, if it links with a conductor loop, see, there is no loop, you cannot see the current. There should be a loop for you to see the current. So if I have a conductor loop which is not moving, or in other words steady, it's not moving, it's a steady conductor loop, but this loop is linking. Linking means this field is passing, or this flux is passing through this conductor. That is what linking means. Here you see, this first one, this is the first case and the second case of the third relationship. We are discussing the third relationship, where we have a steady magnetic, I may have a steady magnetic field, or I have a changing magnetic field. If I have a steady magnetic field, also I can produce current, but the condition is there should be some flux cutting action. That means this is flux cutting action. Flux cutting action should be there. Or if there is no flux cutting action, that means the conductor loop is steady and the magnetic field is steady, then there will be no current produced. But if the conductor loop is steady and the flux that is linking is changing with respect to time itself, then I can say current will be produced. Then I can say current will be produced. Okay, so this is very, very important. Now, from this particular statement, here the law that we get is called Faraday's law. Right? We all know this law, which is very, very important and very, very familiar law for science students, which is Faraday's law. Now what does Faraday's law says? Faraday's law explains the phenomena of this particular experiment. What he says is that the current is produced because some EMF is induced in that particular coil. And he says he will give the relation between the EMF which is induced and the reason why that is induced. So he is saying that EMF will be induced whenever there will be flux cutting action or flux linking in such a way that flux is changing itself. Or in other words, we can say that EMF is induced in a coil, and that EMF is nothing but the rate of change of flux, and say there are number of turns, n turns in the coil, so we'll have number of turns n also. Okay, so that means I am saying that if I have a, say if I have a coil in this way, and if there is n turns in it, okay, and this particular coil, okay, is linking some flux phi, which is changing with respect to time, which is given by this d phi by dt, then some EMF is induced in this particular coil, and this particular, suppose this is A, this is B, so this EAB, this EMF induced EAB can be given by this particular expression, and this is called Faraday's law. Now you see, there is one more thing here. This is giving us the magnitude. Okay, this Faraday's gives us the magnitude. It does not give us the direction. There is one more law which is called Lenge's law. Now Lenge's law gives us the direction. But Lenge's law is actually, Faraday's used this Lenge's law. Lenge's law is a very generalized law. It's not that Lenge's law is given this for this particular electrical concept. Lenge's law is a generalized law, and Faraday's used this law in explaining his law. And what Lenge's law says is that the effect will be opposing the cause. Okay, so here the effect is nothing but that EMF which is induced, and the cause is the change of flux. Okay, flux linkage. So that means I'll have a minus sign here. Okay, that means it is opposing to the change of the flux. Okay, so this complete together, I can say this as Faraday's and Lenge's law. Okay, so now suppose if a particular situation is given, okay, if a particular situation is given, then how to find out the direction of the EMF which is induced. Okay, so you see, by using that Faraday's law, this particular law, we can define a convention which is called Fleming's right, you can see in your PPT also, right hand convention. Fleming's right hand convention. Now we use this convention to find out the EMF which is induced in a particular coil, which is having either flux cutting action or which is having a linking a flux which is changing with respect to time. Now to find that EMF, let us take an example. Suppose I have a north pole here and I have a south pole here. Okay, and this is the direction of my field. As we all know, that fields will flow from north to south outside the bar. Now at this particular point, suppose I have a conductor. And this conductor is moving in this direction. So this particular, and I have a conductor here who is moving in this particular direction. Okay, so what will be the direction of the EMF which is induced in this particular conductor? Now you see, this particular phenomena is nothing but, it's a phenomena of generators. So we use this Fleming's right hand rule for generators, which you can note it down. Generators. Okay, that means we need to find out the EMF which is generated or which is induced in this particular conductor. You see, Fleming's right hand convention, you can see in your PPT also, that we will use this forefinger. Okay, this forefinger will use this thumb, and we will use this second finger, and the positions will be in this particular way. If you can see, it will be in right angle with respect to each other. Second finger. Now this forefinger, the direction of my forefinger will be the direction of my field. field from north to south. Okay, field from north to south. The thumb is going to give or going to represent the direction of the force. Direction of force or torque, you can say. Direction of torque or force. Here you see the direction of force or torque for this particular conductor. Let us say this is A conductor and this is B conductor. For A conductor, the direction is upward. The field is this side. So if you place the thumb along the force and the forefinger along the field, so you will get the direction automatically, which is, we can see it is inwards. So we can say, or we can denote it by giving the direction of the EMF which is induced here by cross. So second finger gives us the direction of induced EMF. Okay. Similarly, in this particular case, I'll use the right hand and my field is in this direction. My conductor is moving in this direction. So my EMF will be outwards, which is nothing but dot. Okay. So this is my Fleming's right hand convention. Okay. This is very important. This particular convention is very, very important when we will be studying DC machines. So you see, this is the concept which I was saying, that from this particular statement we can, or in other words, from this particular statement, DC machines have been evolved. Okay, DC machines was evolved. Or not only DC machines, what I mean to say was generator was evolved. Whether it is DC or AC doesn't matter. The concept of generator was evolved from this particular statement. Okay? Concepts of generators was evolved. It may be DC or AC. Now, from the Faraday's law, we can also define one more property of a coil, which is called inductance. Okay, so inductance is a property of electrical conductor. You can see in your PPT, it opposes the change in the current. Okay, the change in the current. So if I have a coil with some N turns, if I have a coil again, say with N turns in it, and current IT is flowing, and this I is changing with respect to time, then this inductor or this inductance of this particular coil will oppose the change in this current. Now, you see, we can find out the expression for that inductance also. So we can say that, or it is said that EMF which is induced is proportional to the rate of change of current also. Okay? This is the same EMF which we say that EMF is equal to N d phi by dt. See, here I am just taking the magnitude, so I am not, so this is just the magnitude which I am bothered about. The negative sign I have not considered here. Also you see, this E I have said is proportional to di by dt, and inductance of that particular coil is nothing but the proportionally constant. Okay, proportionally constant for this particular expression is inductance. So inductance is given by L. Okay, now I can equate both of them. Okay, and by equating and integrating both of them, what I can say is E is equal to Li, okay, is equal to, after integration I am getting this, Li is equal to N into phi. Okay, Li is equal to N into phi. That means I am equalizing this two and then integrating. After that I can say L is equal to N into phi by I. And what is phi? Phi, I know it is nothing but MMF by, so I can say that L is equal to N by I into phi, and phi is nothing but MMF by reluctance. MMF is nothing but N into I again. Okay, and reluctance. What is reluctance? If you remember, reluctance I can say let us say this is S. So it becomes, this I will get cancelled. So it will be N square by reluctance. Okay. And we know what is reluctance, expression of reluctance. We can also, instead of putting S here, we can put the expression of reluctance also. The expression of reluctance we know is L into mu into E. So I can say this is the inductance of the coil, okay, or solenoid, we can say. And this L is the length of the solenoid or length of the conductor. A is the area through which the flux is flowing. Area of the, say this is my coil, so area will be perpendicular to this particular coil. Okay. So this is the property of inductor, which is this is inductance is defined from this particular state. Okay. There is one more last statement which we can also derive from the relationship of current and magnetic field, and that particular statement is, what if we have a magnetic field as well as a current carrying conductor? What then? So that gives rise to a fourth relationship, which says in a steady magnetic field. That means, now what I am saying is, suppose this is a fourth relationship. I have a steady magnetic field, and I have a current carrying conductor. Current carrying conductor. Now what will happen? Earlier what was happening is, if I am giving steady current, I am getting steady magnetic field. If I am giving steady magnetic field and I am changing or I am moving my conductor, EMF is induced or current is flowing. If I am having a changing magnetic field and my conductor is steady, then also EMF will be induced. Here what I am saying is, I have a steady magnetic field and my conductor is moving in that particular, I have a steady magnetic field and my conductor is in that magnetic field and it is carrying current also. Then what? Then what will happen is, this particular conductor, if it is present in this particular magnetic field, then what will happen? It will experience a force. Okay? It will experience a force, and that force can be given by Lorentz force. Okay, that force can be given by, that is called as Lorentz force. Now you see, the expression for Lorentz force, we know is F is equal to Q into E plus Q into V cross B. Okay. Now this particular expression is true if I have a coupling field which has both electric field as well as magnetic field. Now this force will be generated for electric field, electric coupling field, or you can say. And this force will be generated for magnetic coupling field. Okay. Now, in our electrical course or electrical machines course, we are only dealing with magnetic field, right? So whenever we will use the force and all, so we don't have electric field, we will not use this particular term. So for us, the force is Q into V cross B. And this particular thing can also be written as Q or B I L. Okay, or L, if you want to write it in cross product terms, it will be L into I cross B. Okay, it can be easily derived here by relation. There is a relation between Q and I, there is a relation between L and V. L is nothing but the length, V is nothing but the velocity with which the conductor will be moving by this particular force. Okay, so this is an easier term. So what we will do is we will use this particular term as the force, BIL. Okay, if the direction is perpendicular, okay, we know sine 90 and 90, if it is the angle between them is 90 degree, we can say it is BIL. So the maximum force that can be produced is BI into L. Okay. Now the last thing that we have to understand, or we should know for this particular topic, is to find out the direction of the force. In the earlier one, what we did is we used Fleming's right hand rule, and using this Fleming's right hand rule or convention, we know that there we needed to find out the direction of the induced EMF. What we knew was, we knew the direction of my field and we knew the direction of the force. And by using Fleming's right hand rule, we found out the direction of the induced EMF. In this particular situation, what we have is, we have the direction of the current, we have direction of field, so we need the direction of the force that is generated. And you see, this is what happens in a motor. Okay, in a DC motor, let us take an example of DC motor. So what will happen in a motor is, there will be north pole and south pole, and conductors will be there. Now these conductors will have, say, the current direction will be in such a way. So what will happen is, I will expect that this conductor rotates. I'll expect that this conductor rotates. Now this will rotate when, or this particular rotor will rotate when it will experience, the conductors in that rotor will experience a force. Now they will experience a force. Now we know that whenever there is a field here, and in that particular field I have a current carrying conductors. In this particular field I am having current carrying conductors. This conductors is going to experience force. Now let me find out by Fleming's left hand. Fleming's left hand rule. I'm going to find out the direction of the force. And so I will use this convention only in case of motors. Okay, so this is beneficial for finding the direction of rotation of my motors. So you see, this is the direction of the field, this outside, right? So it is coming out, so let us go in this one. So it is coming out, means this will be the direction of my current, and so this will be the direction of my force. So this is the direction of my force for this particular conductor. For this particular conductor, you see, current is going inside. So second finger will give me the current direction, it is going inside. First finger, forefinger is going to give me the direction of my field, which is in this direction. So this is that. So the thumb is giving the direction of the force, which is coming down. So this is the direction of my force. Now we know, due to the equal and opposite force, I will have a torque in that particular rotor, and it will start rotating in anti-clockwise direction. So this is the application of Fleming's left hand rule. Okay. So once we understand this particular four rules or four relationships between current and magnetic field, now since we have understood the relationship between this current and magnetic field, we are in a position to understand the complete electrical machines. Okay, so we are done with the rules and conventions which are required to understand the machines, all the electrical machines.